All right, let's move on to section 7.2, line termination with arbitrary load. So again, we'll look at the transmission line problem in the frequency domain. In section 0.1, we look at the situation, the case of short termination. Now we can have an arbitrary termination. It doesn't have to be short or open. It can be a load of any value. And name any value suggests that it can be a resistive load or a reactive load or a load with both resistive and reactive parts. Okay? So we just label it as ZR, as the termination of the transmission line. And again, as long as the termination, the impedance of the termination is not the same as the characteristic impedance of the transmission line, which is labeled as Z sub 0 here, there will be both forward going and reverse going signals on the line. So you will have V plus signal, V minus signal, as well as I plus and I minus signal. So again, we can write down the total voltage and total current on a location on the transmission line. So you write down equation 7.18a and b, which are voltage and currents on the location of D on the transmission line. Again, you can see there are summation of forward going and reverse going components. So both voltage and currents are summation of the two components, forward going and reverse going. And what is the boundary condition? So now the boundary condition is the relationship of voltage over current, which means at the D equal to 0, the voltage must be ZR times the currents on the line. So if the load is purely resistive, then V and I will be in phase. They will have no phase difference. On the other hand, if ZR is a complex number, then it suggests the voltage and current shall have a phase difference. They will not be synchronized. They will have a phase difference. So we have the boundary condition specified in equation 7.19. So you substitute V of 0 and I of 0, the voltage and current at D equal to 0 using 7.18a and b. So that will be, the total voltage will be V plus V minus, and the total current will be V plus minus V minus divided by Z sub 0. And if you massage this equation a little bit, you can find out the ratio of V minus over V plus equals to ZR minus Z sub 0 divided by ZR plus Z sub 0. Don't you feel that this looks familiar? This relationship looks familiar. This is the definition of reflection coefficient. Now the loading we observe is replaced with ZR. Okay? Well, that's the impedance. You look into the right, at the very right end of the transmission line. So again, you can define the reflection coefficient. You can find out the reflection coefficient at the right end of the transmission line, and it looks like this, the relationship that you already memorized. And by definition, it's the ratio of reverse going voltage over forward going voltage. So let's examine a few cases. If ZR equals to Z sub 0, that is the so-called match load, then the reflection coefficient will become 0. And if ZR equals to 0, which is the case of short termination, then the reflection coefficient becomes -1. So what happens if you substitute ZR with infinity? Well, that is the case of open circuit. Then the reflection coefficient gamma will becomes infinity divided by infinity, and it's +1. So for open circuit, the reflection coefficient is 1. And with the definition of reflection coefficient, what can we do next is replace V minus as the product of gamma R times V plus. And you can do the same thing for the current part. So in equation 7.21a and b, the V minus signal is replaced with the product of gamma R times V plus. Not that the reflection coefficient gamma R is also written in the phasor form. It's also written in the phasor form. So it's frequency dependent. You can say that it's frequency dependent. And it's a complex number in general. Gamma R is a complex number in general. So we now define the generalized voltage reflection coefficient gamma D, which means you don't have to stay on the right end of the transmission line. You can move your observation point any place on the transmission line. And for any place on the transmission line, you can define the so-called reflection coefficient at that particular point. So gamma, the reflection coefficient, can be a function of D, a function of position. D is not necessarily 0. If D equals to 0, you can specify it as gamma R. So gamma R is the reflection coefficient right next to the termination. And gamma D is the reflection coefficient. Note that gamma D is still defined in terms of reverse going voltage over forward going voltage. But that will be what? That will be V minus D over V plus D. So if you write just V minus and V plus, you are referring to the voltage at D equal to 0. So gamma R is also the reflection coefficient for D equal to 0. And this will be defined as gamma D. Okay. So if you substitute V minus with gamma R times V plus, then the gamma D becomes gamma R times exponential minus J times 2 beta L, 2 beta D, 2 beta D. Why? Because in the denominator is exponential minus J beta D, and in the nominator is exponential plus J beta D. So if you collect the two terms, it becomes exponential minus J 2 times beta D. So this is the definition for reflection coefficient at any place on the transmission line. It can be interpreted as the reflection coefficient at the termination times the effect of the transmission line, which address the phase change on the line. You see there is a 2 over here, so it take into account forward going and the backward trip. So it's a round trip effect. D is the length of the observation point to the end of the transmission line, the distance. And you will eta 2 over here to account for the round trip effect. And the gamma D in general, the phase, so this is the magnitude of gamma D. Gamma of D, this is the magnitude of gamma as a function of D. Not that it equals to the magnitude of gamma R. Why? Well, there is an assumption that we need to make before we proceed for the discussion here. That is, the transmission line is lossless. This is a lossless transmission line, so there is no loss on the line for signals on the line. Okay, so the change only include the change in phase, not in the. You don't have change in magnitude because this is a lossless line. So the reflection coefficient are the same once you fix up the termination. So the magnitude of the reflection coefficient at the d equal to 0 and any other value of d are the same. However, if you check up the phase of the reflection coefficient at a different position, they are substantially different. Okay, so here is the reflection coefficient phase of gamma as a function of gamma of d. It can be expressed as the phase of gamma r plus the phase of this term, which turns out to be what? 2 times beta minus 2 times beta d 所以后面这个 exponential 它的角度是什么？就是它的那个指数的部分除掉那个 j 以外的指数部分所以只要你的这一个 exponential 是 exponential minus j 2 times beta d 的话，它的角度就是 minus 2 times beta d。那这个 theta 指的是前面 gamma r 的角度所以你的反射系数，只要你是在无耗损传输线上面的话，不同的位置它所看到的反射系数大小都相同，因为没有耗损，但是它的相位会随着不同的观察位置而有所变化，而这个变化量是可以算出来的就看你的观察位置离终端有多远那个位置就是 d 嘛，那个距离就是 d， 然后 d 乘上2嘞就是 round trip 的那个距离，然后再乘上贝塔所呐含的是什么效应？这一个在传输线上面跑的讯号的频率所以贝塔其实就是什么 2 pi over lambda 嘛所以它是算出来你那个距离 d 跟 lambda 的比值它相当于几个波长相当于几个波长就给你多少的相位变化 OK So once you have determined the value and type of your termination, the reflection coefficient magnitude will become a fixed number. On the other hand, the phase of the reflection coefficient shall change as you move your observation point. All right? So the reflection coefficient magnitude is a fixed number, but the phase changes as you move the position d. So in terms of gamma d, we can write down the solution for Vd and Id as this. So now we try to replace the second part of the small parentheses as gamma d. Well, actually this represents the component of a reverse going wave. So the 1 stands for the forward going component, and the second term stands for the reflected wave. So equation 7.24a is the total voltage. The total current is expressed here. You see there is a minus sign over here for the current expression. And the next thing The next things we would like to examine is the change of VD, the change of VD signal. Okay, and we know it's a standing wave. It shall exhibit a standing wave pattern. Why? Because the termination is not a match load. So some of the input signal are reflected back. So as long as you have a reverse going component of the voltage and current, you shall have the so-called standing wave. You will have the standing wave. And if the termination is short or open or purely reactive, then you will have the so-called complete standing wave. On the other hand, if the termination is somewhat resistive, which means some of the incident energy is absorbed by the termination, then you will have the so-called partial standing wave. But anyhow, no matter you have complete standing wave or partial standing wave, it turns out that the largest voltage you observe on the line will change as you move on the transmission line. So different places will exhibit different voltage and current amount as long as there is a standing wave. There is a complete standing wave or partial standing wave, you will observe that the voltage value goes up and down at the different places. This figure is probably one of the most difficult one to explain in our textbook. On the other hand, if you can understand this plot, you will have no problem understand what the content of this section. So we probably